Good afternoon, all. Good afternoon. Okay, so I have started to share my screen. I think you all can view it. Let us begin our session with the recap of last session. Yes, yesterday we were talking about error detecting code, and in error detecting code we have discussed about parity bit, then checksum method, and block parity method that can be used to detect the error whether it is present in your code or not. They all will have some advantages, disadvantages, some limitations that we have talked yesterday. And at the end, we were discussing about error correcting code, that is a 7-bit Hamming code we have discussed. And in that, we have seen that how a 7-bit Hamming code can be used to determine that which of the bit of your code is get effect of noise, or we can say it becomes from 0 to 1 or 1 to 0. So that is what we have discussed yesterday. Now, in our today's session number 11 from the chapter 1, Fundamental of Digital System and Logic Family, we are going to begin with our Boolean Algebra part. So, this will be the learning outcome of today's session. In our today's session, we are going to discuss about various laws of Boolean Algebra that we can use to reduce, or you can say simplify the Boolean expression. One of the theorem which is most famous in case of Boolean expression reduction, that is the De Morgan rule, which we also came across in the laboratory session. So that also we'll be discussing here. And then after we'll be taking the examples of this Boolean expression reduction based on application of all these rules in that. So let's move inside the Boolean algebra part of this chapter. So we begin our session with the various laws. So first of all, what do you mean by Boolean algebra and Boolean expression? See, as I already told you in that when we talk about a digital circuit, that digital circuit is required to perform various logical tasks and arithmetical tasks, right? Now, to achieve that logical and arithmetical task, you require to form a digital circuit. There are two types of digital circuit which we can form. That is, one is combinational logic circuit, and other one that will be a sequential logic circuit. We will come across a sequential logic circuit later on, but right now let us talk about combinational logic circuit. So combinational logic circuit means what? It is a circuit which will be developed by making a combination of various logical gates. Right. In laboratory session, we already came across like how can we develop a half adder circuit, how can we develop a full adder circuit or full subtractor circuits, right? So that we already have understood. And there we have seen that though your half adder, full adder or subtractor is the arithmetical task, but that arithmetical task can also be realized by using the various combination of logical gates. So here Boolean word is stands for the signal which will have only two level of signal, that is you can say two level of magnitudes, either logic 0 or logic 1. That's why the word Boolean stands for here. And Boolean expression means the Boolean expression will give you that what kind of logical combination of the various gates are required to perform this output or to get this output. I hope you can understand. For example, you have some three inputs, let's say A, B, and C. Okay, and I want to get my output in such a manner that when A and B both are logical 1 and there is a C input is also present, but I do not care what the value of C is. Okay, so I just want my output equal to 1. Let us say if I just give you here, Okay, suppose I give you an example that I have three inputs A, B, and C. Okay, this is what you can have three sensor signals or anything. Okay, so this three information I do have for my system, and this system giving me one output. Now this output Q of the system, what I required is, means my system here is required to perform, or it required to do some process on these three inputs in such a way that it will give me output here only when my input A and B, they both should be 1. Whether C is 0 or 1, that I do not care. Okay, so this is what my requirement is. Now why this requirement is, we are not going in that detail, but right now to understand the meaning of Boolean expression, you can understand this part, that you have a system, or you have some circuit, or you have some logical task which is getting three inputs A, B, and C. I want to get my output Q, that is logical 1, only when my both the input A and B are logically 1. Right? Whatever the value of C is. If A and B is 1, then my output Q should be 1. But if any one of this is 0, let us say A is 0 and B is 1, then my output should go 0. So my output Q required to get value 1 only when A and B both are logically 1. So if you want to represent this task in the form of equation, in the form of expression, so how can we represent that task? That is called Boolean expression. So I can give here Boolean expression for the Q like that, or it will be irrelevant to your input combination, that I will be writing it like this, that it will be A, B plus C. I can write it like this, right? What it means that if your A and B is 1, I should not say here C also actually, because it does not depends on C. So I can remove that part C, because if C is not going to be there at all on the equation, I can remove the part C also from here. I can just have my Q equal to AB. That is, AB means the AND operation of A and B. Now whatever value of C that I said, I do not care whether it is 0 or 1. It's not affecting your output Q. That's why I'm not taking in the expression here. So I can say it will be Q equal to A and B. Okay. And now suppose if I say that my system is required to be giving me output Q equal to 1 when A and B both are logical 1, as well as your output C should be 0 at that time. I hope you're getting it. When I say what I need is, I want to develop a system. This is my system I want to develop. Okay. And that system performs what? It will check your input, and based on the input availability, it will decide what output Q should be. So first case I told you that I want to get my output Q equal to logically 1 if and if only your A and B both are logically 1. That there is no dependency on the input C. So that's why this is what the expression for the Q you have. But now the second case which I am talking, in that case I want to get my output Q to be equal to logically 1 when there is A and B both are logically 1. That is the first requirement. And the second requirement is that your C should be 0. So what you have to write here for Q in that case, that your first thing is that you require to get your A and B, that both should be logically 1. But what is the third condition we required? That your C should be 0. So I can write down here like that, it will be C bar. So this will giving you the AND operation of your A, B and C bar. So 3 input AND operation will be there. But here you have to take C bar because you required your output Q equal to 1 when C equal to 0. So C bar will become 1. So when A and B both are 1 and C equal to 0, only for that case this expression will give you logic 1. For remaining all other cases it will give you output 0. So in this way, depending on your number of inputs available and depending on your logical task required to be performed to get the particular output, you can express that all logical task with this kind of formula, and that's what we can say it's a Boolean expression. Am I making this thing clear to everyone that what the meaning of Boolean expression is? Hello everyone.
Yes, sir.
Yes, sir.
Yep.
Okay. Still very much less students are available here. Many of you have not joined yet. Anyway, so I just made you clear about the thing that what do you mean by the expression, or you can say Boolean expression. Now the second thing is that what do you mean by Boolean algebra? Boolean algebra means what? Based on your requirement of your system, you have written down your Boolean expression. Now that Boolean expression will be requiring so many combinations of logical function. So that logical function we can reduce to a smaller size of expression so that it can be implemented using lesser number of logical gates. Right? If you have a very long expression written having so many tasks in that, if you are able to get the same task by having only small logical performance, then it will be better for us to implement with the help of logical gates. So for that, what you need to do is you need to reduce your given Boolean expression in such a manner that it will not affect the required logical task, right? So that is what the consideration in the Boolean algebra. So Boolean algebra is what? It is the method, or you can say it is the rules which you can apply on your Boolean expression to reduce it in a smaller size so that it can be easily implemented using the small number of logical gates. So that is what Boolean algebra is. Now for that Boolean algebra, or you can say to perform that Boolean algebra, you require to know various logical rules, or you can say various Boolean algebra rules or laws that can be applied on the Boolean expression to reduce it into the smaller size. So what that is, let me just tell you here now. So we are going to now start with the Boolean algebra law. After knowing the Boolean algebra law, you can be able to reduce any given expression in a smaller size as much as it can possible. So first two laws are, you can say, AND laws and commutative laws. AND laws means what? You can see here there are four rules it is written. First one here written, it is when it is AND operation of any input A with zero logic, it will give you zero output, right? And that we can easily understand, because you know, if you have the AND gate, for example, if you have been given the AND gate, right, and here are the two inputs. Suppose one input I am giving, that is A, and other terminal I am giving 0. 0 means it will be always 0, right? I am not writing down any variable there. It is a constant 0 input at the other input. That means what? This AND operation is going to be performed between this A and 0. Now you know the logical truth table of this AND gate, that it can give you output logical 1 only if your both the inputs are logical 1. But here you can see that one input you have made continuously 0. Always it remains 0. That's why whatsoever the value of A is, whether A is 1 or 0, it does not affect your output. Your output remains 0 only because your second input is 0. And that is what the first rule here saying you, that if you are making AND operation of your any input with 0, that is A dot 0 will be giving you output 0. Similarly, if you are performing AND operation to logical 1, then it will always give you whatever your signal input is. Now you can see in this same input, instead of 0, if here I give one logic continuously, and if I apply input A on other input here, so what will be the output? You can see if your A is 1, then this input is already 1 and your A is also 1, so both will be get 1, so output is going to be 1. But if your A is 0, then this is already 1, so 0 1 gives you output 0. That means whatever the value of A is coming at the input side of this AND logic, it will give you the same output. That's why it is here written for the second rule, that if you perform the AND operation of your any input with the logic 1, then your output will be equal to whatsoever your input is. Here for that A dot 1, it will give you output A, and that is what we call it is identity rule or identity law. That is, AND operation of any signal with logic 1 give you same signal, identity. Likewise, third rule, that if you perform the AND operation of the two inputs with the same number, same variable, it means in here, if I apply A here also in the second input, if my AND gate is given with the logic A only, both the inputs here also A and here also A, then what happens? If here going to be 1, here also going to be 1, because both the signals are same. If 1 1, then output is going to be 1. If here I give A 0, then here also it's going to be 0, so 0 0, output is going to be 0. That means whatever input you will be giving, same kind of output you will be getting. That is, if you are performing AND operation of any signal with the same signal, then it will be coming equal to that what signal you are performing AND operation. And the similar way, another AND rule is that if you performing AND operation of your any signal with its inverted signal, A dot A bar. A bar is what? It is the inverted signal of your A. If your A is 1, then A bar will be 0. And if your A is 0, then A bar will be 1. Right? So that will also give you answer 0 always, right? Because they never going to be same 1 at a time. And for AND operation, they both should be 1 to get output 1. And that will never achieved in this case. And that's why you can say your A dot A bar will always give you output equal to 0. So this is called AND law, or you can say AND logic performance rule. Second thing is that commutative law. Commutative law means if you are going to perform A or B, that is A plus B, it means you performing OR operation between A and B. It is equivalent to you perform OR operation between B and A, right? That is, in your OR logical gate, if you apply first input A and second input B, or you apply first input B and second A, that doesn't matter, your output remains same. That is what you can say commutative law, right? Same way you can apply that for the AND rule also, that whether you perform A dot B or B dot A, they will not giving you different output, they will be giving you constant or you can say same output. That's called the commutative law. Now third category, that is what we have is OR law. Now OR law means it is the OR operation of your signal with 0, 1, that particular signal and inverted signal, similar to AND law we have discussed. So here you can say the same thing with the OR gate, right? As I explained here with the AND gate, same thing you can discuss for the OR gate. Now you know, if you are performing OR operation of your input A with logic 0, now here you have to have your mindset with the logical truth table of OR gate. We know that OR gate is giving you output 0 only when your both the inputs are 0, right? So if your signal A is 0, then they both will become 0. So your output will be 0. So what it is equal to A there. If your A is 1, then A OR operation with 0, that is 1 0, it will give you output 1. That means whatever value you set for A, that same will come at the output if you are performing OR operation of A with logic 0. And that's why you will be getting the output same, whatever it is there at the input side, A. Same way if you are performing OR operation of logical 1. Now when you are performing OR operation of your A with logical 1, your one input of OR gate is always going to be 1. And that's why whether your A is 0 or 1 doesn't matter. Your output is always going to be 1, right? Third case is OR operation between the signals. So they both can be 1 1 or they both can be 0 0, right? If they both are 0 0, then also your output getting 0. And if they both are 1, then output is 1. That means whatever the value of A, that same will come at the outputs. And that's why it is A plus A can be equal to A only. And the last one for the OR law is that A plus A bar. So here you can see if your A is 0, A bar will be 1. If A is 1, A bar will be 0. But out of these two, A and A bar, any one of them will remain 1 always, right? Either your A bar will be 1 or A will be 1, and that is why the OR operation will go to give you output logic 1 there. Right? So that's what the OR laws you can say here. Now, the fourth category of rules is associative law. Now, associative laws is what? Here you can see if you are going to perform the OR operation of A, B, and C, three inputs, and you want to perform this OR operation with, let's say, two OR gates. Right? Suppose I have the two input OR gates only. So this is one OR gate, and I have another OR gate here, let's say. Okay, so I can do like this also. That means I will perform first OR operation of A and B, and whatever output I am getting, that I will give at the input of another OR, and the third input will be given here. So finally what I will be getting here is A plus B OR operation, and that is OR with the C. So this is also giving you the output same. If you perform like this, that if you perform first B and C OR operation, right? If you can do like this, you can make the OR operation of B and C first, and then it will be output going to be OR with A. That is called associative rule, right? Whether you can first do A, B OR operation and then your output can be OR with C, or you can perform first B and C OR operation and the whatever output you are getting, that is going to be OR with the input A. They both will give you the similar output. So there is no change in that, and that's what we understand as the associative rule. Likewise, that same can be there in the AND operation also. If you want to perform AND operation between A, B, C, all three inputs, then you can do first or AND operation of A and B. Then whatever output is coming, you can do the AND operation with C. Or otherwise, you can first perform AND operation of B and C. And whatever output is coming, then you can end with the A. So they both also can give you the same output. That is called the associative law. So these are the few laws we have discussed. Any doubt to understand these laws, or all are you getting this? Yes, Pujan, have you understood it?
Hello.
Hello.
757.
Hello, Pujan, are you there? Have you understood this clearly? Use your unmuted and give your voice here, there. Yes or no? Anyway, Nihil, are you there? Hello, Nihil. Can you hear me, Nihil? I want your feedback. Have you understood it or not? Hello, Nihil. Am I audible to you? Yeah, be quick in response. Okay. And use your unmuted tab in your Google Meet, so you can give me answer by just your voice message there. I told this thing yesterday also and many times before also, that instead of typing your answer in chat, it's better that you give me answer by your voice message. Okay, anyway, these are the few laws we can use in the Boolean algebra to reduce our expression to a smaller one. Now, let's move to the next part. That is another set of Boolean algebra laws. That is, first one is distributive law. That is, if you have been given that you perform this expression A in bracket B plus C. That is, you can say first you have to perform OR operation of B and C, and then it is going to perform AND operation with A. Okay. Instead of that, what you can do is you can do the AND operation of A and B. That's what here, and you can do the AND operation of A and C. It is just like we are opening the bracket in any expression, right? So that will be also okay. So this expression will give the same answer. That is, whether you perform OR operation of B and C on the left side, right? This is, you can say, LHS. So on LHS side, you can say performance of B and C OR operation, and then whatever output is coming, you are getting AND operation with A. If you do that, that will give you LHS side. And if you perform this on the RHS side, right hand side, that is, you can say if you perform first AND operation of A and B, and then you perform AND operation of A and C, and whatever output coming from both, that you have to get a OR operation. That is, both will remain same. That is what your distributive law is. Same kind of distribution there for A plus BC. Here you can see BC is giving you AND operation between B and C. So you can do first AND operation of BC, and then you can do the OR operation of output with the A. Or otherwise, what you can do the A or B first, then you can do A or C, and whatever outputs are coming, then you can do the AND operation over here. Right? So this both will also give you the same answer. That is what your distributive laws is. Then after idempotent laws, what it is, we already have seen about this too, right? If you make an AND operation of A, that will give you output A only. If you perform OR operation of A with A, it will give you A only, right? This already we have seen in our AND laws and OR laws, but this is just separately written over here. Now other rules are redundant rules and absorption laws. What it is, if you are performing A plus bar, here you can see, here, first one, A plus A bar B, right? That can be written equal to A plus B. You can give the proof of this also. Suppose I want to give the proof of this A plus A bar B. I can just apply this kind of distributive rule here, right? If I just apply this rule, distributive rule here, that for A plus A bar B, what can I write is A plus A bar B is the expression on left hand side. I can apply the distributive rule and I can do it like this, that it is A plus A bar, right? First I will do this, and then it will be having an AND operation with A plus B, right? Now various AND laws you can apply here. A plus A bar, that is the OR rule. You know that A plus A bar will always give you 1. You can have the 1 AND operation with the A plus B. Now there you can apply AND rules, which we have just discussed. That is, AND operation of any signal with 1 will always give you the same signal, that is A plus B, and that is what your output is. So this is how you can get your simplification, and that is what you can say proof also, right? So that A plus B will come here like this. So that is what I have shown you, the proof of A plus A bar B. That is called redundant retrace rule. So you can, it is just a name. Unless you remember the name, you remember the law. It's better thing that if it is A plus A bar B, it can be written equal to A plus B. Likewise, you can have this one also, that if you are having A AND operation with A bar plus B, then it can be written like A into B. This also you can give the proof by applying this associative rule, first one, right? I can write like this, A into A bar plus A into B, right? And that will be making A into A bar 0. So I will be getting answer equal to AB. So that's also you can do at your own, that how can we give the proof for this formula, redundant rule. Then after absorption rule, if it is A plus AB, then if you do like this, that is if you apply this kind of distributive rule here, then it will make A plus A into, you can say A plus B, like this here you can say, right? Here it is A plus AB, and that can be written equal to A. How is it? You can just apply the proof here if you want to give that it is a plus a into, it will be a plus b. Just a minute. Okay. I think there is some mistake in this rule. Is it okay or not? Because here a plus a will give you answer a, then it will be, yeah, it will be a dot a plus b. Okay, one step more we have to go here. Yes, yes. Okay, so now further you can apply this rule number 1 of distribution, that you can do a dot a. It will be coming again same, I think. Just a minute. Okay, let me do one more thing here about giving the proof for this rule. Instead of going with this Boolean expression reduction, let us me give the proof of this rule by using truth table. That will be better for this one, because I think this reduction going to take much time here. So I will be doing it later on. Let me give the proof of this absorption law with the help of truth table here. So if we take the truth table here, suppose here it is given input A and B, so you have the two inputs, right? And we are having the expression, that is we are making OR operation of A plus AB. So for that, first you require to do AND operation of A and B. and then you can do the OR operation of your A with AB. Right? That is what your output on the right hand side. Okay, and now let's do it. So here you can see your input can be 0 0, 0 1, 1 0, and 1 1. Right? This is the possibility for input A and B. So when you get A B, that is the AND operation, you know they will give you 0 for all except when they both are 1. So this is what your AND operation of A and B. Now if you do the OR operation of your A B with input A, then you can say your OR operation will give here A with AB. So AB is here and A is here, that is 0 0 1 1. So this rule first here 0 0, so it will give you 0, 0 0, so it will give you 0. Here 1 0, so it will give you 1, and 1 1, so it will give also here 1. Okay, so you can see here the output which we are getting for A plus AB, it is similar to that for your A, right? That means you can say here LHS is equal to RHS for this rule, right? So this is how you can give the proof with the help of truth table also. Same kind of proof you can give for the second rule of absorption law also there. I will give you this method for this expression reduction that will give you from LHS to RHS, that is A plus AB, right? And from that A plus AB we can reduce equal to A. So that I will be showing you later on. Right now we just keep this proof, that is with the help of truth table what we have just discussed here. Okay, so these are the Boolean algebra law that you need to use in the case of Boolean expression reduction. So is this part is clear? Keep point of this absorption law reduction or its proof that I will be giving you later on. Right now I given that proof with the help of truth table. So there are two methods of giving proof for any law. One you can give with the help of this kind of truth table arrangement, or second one that you can give as I shown for this distributive law here, right, for the redundant rule. So that is with the expression. So am I making this thing clear to everyone?
Yes, sir.
Yes, sir.
Okay, okay, that's fine. Now let's move next. That is the De Morgan theorem. This rule or theorem we already have discussed in our lab session. So what is this rule is? Basically these rules are two category. First rule is here, that is A plus B bar. That is, you can say a NOR operation of A and B can be equal to AND operation of A bar and B bar, right? On left hand side you can see, left hand side of equal sign, we have NOR operation of A and B, that is A plus B bar. On the right hand side it is AND operation of A bar and B bar. That is what we have already understood, that break the line, change the sign. This is the rule here we have. So if in the form of logic diagram, if we want to see, you can see that if you perform the inversion of output of OR, that is here you can see the first, here it is the OR gate, right? So here output, here it is OR operation of A and B, and that is going to be NOT gate, so it will be making your NOR operation. That's what I'm saying. So if you perform NOR operation of your two signals A and B here on the left hand side, it will be equal to, if you perform the AND operation here, right, this is the AND gate, so it will be performing AND operation of your A bar and B bar here. So that's what here it is said, that if you perform AND operation of your A bar and B bar, they both will be equal. That is what your De Morgan's rule is, right? And second rule is, if you perform NAND operation of your input A and B, that is equal to, you are performing OR operation of A bar and B bar, that is break the line, change the sign again, that you can show with the help of logic arrangement like this, with the help of logical gates, AND OR and NOT. So here in the first case you can see that input A and B is applied to AND gate, so here it will be making AND operation, and that applied to NOT gate, so it will be performing A dot B bar. That's what on the left hand side. That will be the same if you perform OR operation of your A bar and B bar. To get the A bar, you have to put the two NOT gates here. So if this will give you A bar plus B bar. So that is what the De Morgan rule is, and we can easily remember that with the help of line, that is break the line, change the sign. So anytime here you can see you can break the line here and you change this sign, so it will become A bar and B bar. Same way here you break the line and the change the sign here at between, so it will become like A bar plus B bar. So that is what the De Morgan theorem is, and the proof of this De Morgan theorem again you can give with the help of truth table like this. Here you can see for the first rule it is A plus B bar is equal to A bar into B bar. So here that is what we are obtained. First two input signals are A and B taken here, that is 0 0 0 1 1 0 and 1 1. First it is done A plus B, that is the OR operation, and then after it's NOT gate, so it will be A plus B bar, that is over here. So what it will be 0 0, then A plus B will be 0, but A plus B bar will be 1. And for all other combination A plus B is equal to 1, so A plus B bar is going to be 0. Now to get the right hand side expression, you require to get A bar and B bar. So if your B is 0, B bar is equal to 1. If your B is 0, then B bar equal to 1, like that. So B is 1 here, then B bar is equal to 0. So we have got the B bar and A bar here. And then you perform AND operation of this one. So your AND operation will give you output only when they both are 1. So you are getting 1 over here. So you can see here in this truth table that this is giving you the same output for A plus B bar and A bar dot B bar, right? So that is what you can say the De Morgan rule is giving you the proof that the both sides of equal signs are same. Similarly, you can have the proof of second rule of De Morgan, that is this one, that is A dot B bar is equal to A bar plus B bar. So in same manner you can understand, and you can see here that your A dot B bar, that is this one, and A bar plus B bar, that both will come same. So you can say here also that your De Morgan rule is giving you both the sides equal. So that you can apply in the circuit, apply in the equation wherever it is required to reduce it in the smaller form. Okay, so is this part is clear to everyone? We have now completed all the rules which we have to use in the case of Boolean expression reduction. So are you able to understand all these rules?
Yes, sir.
Yes. What about others?
Yes.
Yes, sir.
Yes, sir.
Okay. Now let me show you
Yes, sir.
how can we apply all this rule to reduce the given formula or given Boolean expression. So let us see here. Suppose first you want to get the proof. Let us say we take some example with the truth table proof. Right now you have been given this is A plus B plus C whole bar is equal to A bar plus B bar plus C bar. Here again you can say it's a De Morgan rule only, right? Break the line, change the sign. But here it is with the 3 inputs. Previously I have shown you with the 2 inputs. This also you can give the proof like this, that you can take the 3 inputs A, B, C. When you have 3 inputs, obviously combinations are going to be 8, 2 raised to 3. So first you obtain A plus B plus C bar. For that you need to have first A plus B plus C. That is, here it will be, right? Only you will getting 0 when all 3 are 0. Remaining all cases gives you output 1 for A plus B plus C, that is the OR operation of 3. Then you take the NOT of that, so it will give you 1 only when your all 3 inputs are 0. Then after on the right hand side it is requirement of A bar, B bar, C bar. So I will take here A bar, B bar and C bar, which will be inverted of this A, B and C, right? That you can verify here. Then after you perform the AND operation. So you can see here your A bar, C bar and B bar, they are all 1 only first case. Remaining all will give you 0. So here you will be getting this formula. And here also you can see that your LHS and RHS, that is for the formula, is remaining same, and that's why we can say our De Morgan rule is applicable in the case of three input combination signals also, right? Same way, second one, second De Morgan rule with the three input. Again, you can apply in the same order and same manner. That you also have the proof here like this. On the left hand side, you will be getting A, B, C, and that will be not. So it will be getting this output on the left hand side, and on the right hand side you require A bar, B bar, C bar, and then you have to perform OR operation of that one. It will also give you output 0 only when all three are 0, and that is like this. So here also you can see your left hand side and right hand side are same, and that's why you can say that De Morgan rule is applicable in three input case also. It is not limited to only two inputs. That's here. Okay. Now let's we go with the example. So here you have been given the expression that is f equal to a plus b in bracket ac plus in small bracket b plus c into d. Now this expression we have to reduce to get the smaller number of terms in the expression. So how can we do that? For that we have to start with application of all the rules, all the laws, what you can say we have discussed. So let us start with the given function f. Now you need to think on that what can we apply here. There are various laws, AND rules, OR rules, distributive rules, associative rules, right? Absorption rules. So many rules we have discussed. So you can make a list of all that rules, and once you can remember all that rule, it will be easy for you to do this expression reduction. So first of all, what we are doing is, you can see here what we have done. We have applied rule over here, that is b plus c bar into d. So I have just it is a distributive rule we have applied. So you can say b into d plus c bar into d, right? That's what we have applied here. So you can say we have applied the distributive rule. You can write down this kind of thing beside the step, that I have applied distributive rule in this step. Okay. Then after, again we have applied distributive rule, that is your b outside this square bracket we have taken inside. That means we have applied the distributive rule, that your b got multiplied with all that like this. That is again we have applied distributive rule there. Then after, what we are doing, what rule we have applied? One rule we have applied here, that is b dot b, that is AND rule, right? A dot A equal to A. Similarly, B dot B is equal to D. Here we have applied rule of you can say sequence rule, that is either you perform BAC or ABC, that doesn't matter, they both will give you the same output. Okay. Then after, what we have done is, from the first two terms we have taken A common, so it will give you output like this, right? Then after, from the second two terms we have taken BD common, so it will give you output like this, right? So here you can say what we get reduced form is 1 plus BC, 1 plus anything, right? That's what your OR rule is there. So that will give you 1, so it will give you A only here on this side, and on this side 1 plus C bar, so that will also give you 1, so that will give you BD over here, right? So this is what you got the reduced formula for this function, that f equal to A plus BD. Right? Now there is no further reduction can possible, so this is what your last reduction step you can say. So are you able to understand this, that how can we get this reduced form of this Boolean expression? Hello, are you able to understand this?
Yes, sir.
Yes, sir.
Okay, let's take
Yes,
one more.
sir.
Okay, that's very good. Let's take one more example to make you more familiar to the steps of reduction. Suppose you have been given this formula, that your f equal to A in square bracket B plus C bar, in small bracket is AB plus AC bar, then whole bar is there. So now we want to reduce this formula. So how can we reduce it? Just a minute. Okay, so what we are doing here is, let us see the step of solving this. So first step, by starting with the function given, what is the first step we have applied here is break the line, change the sign. That is the De Morgan rule we have applied. You can see here in the last side. Here in this part, we have break this line and we have changed this sign, right? So it will made to dot here, right? And here this bar is divided in between AB and AC bar, right? Then after, again we have applied the De Morgan rule. First for this A and B, we have break this line and the change the sign. So it is A bar plus B bar. Then here break the line and change the sign. So it will be A bar plus C. Why it is C? Because it will be getting C double bar. So it will be directly written over here C. So again we have applied the De Morgan rule here. Then after, we have started to given the associative rule, distributive rule between these two brackets, A bar plus B bar and A bar plus C. So you can say A bar dot A bar here first, then A bar dot C here, then B bar dot A bar, and then B bar dot C. So these two brackets are distributed, and that's why you get this answer. Now next, you take this C inside. So again we are applying distributive rule there, right? So C bar A bar into A bar will be taken A bar only here. So here we have applied that identity rule also here. Then after C bar A bar C, then C bar B bar A bar and C bar B bar C. So C is multiplied with all the terms inside the bracket, and you got this. Then next, you are applying here C bar into C, that is the AND rule, right? Here C bar and C. So C bar into C will always give you 0, so this term will become 0. And similarly here also C bar and C, so that term will also going to be 0. So that two term made to be 0 and remaining two term will be as it is. So that's what here. Now next, here you just taken A inside, so it will be AB first, then A into C bar A bar, then A into C bar B bar and A bar. Now here A and A bar, so this term is going to be 0. Here also A and A bar, so this term also going to be 0. So you will be getting the last answer, that is AB plus 0 plus 0. So final answer is AB. So this is how you can reduce. See, now what is the purpose of reduction of this Boolean expression? If you look at here the given function, that it is f equal to this whole operation you have to perform. Now if you directly go to realize this function using logical gate, what you have to do is, you have to first take one AND gate to make A and B AND operation. You need to take one NOT gate to get the C bar. Then you need to take one more AND gate to get AND operation of A and C bar. Right after that, you require to take one NOR gate to perform the NOR operation of AB and AC bar. After that, you require to take one more AND gate that will be making C bar dot this whole expression. Likewise, you require many number of gates to get this output F, right? But instead of this, if you have reduced this function, you got this expression that is very small. A single AND gate give you the same function output F. Are you getting this? The purpose of reduction of Boolean expression?
Yes, sir.
Yes, sir.
Right?
Yes,
so,
sir.
okay, so that is what the purpose of Boolean algebra. That by using Boolean algebra,
sir.
we can reduce any given formula, any given Boolean expression in a smaller size, and that will make us to realize that Boolean function using smaller number of logical gates. Is that clear? Okay.
Yes,
Okay.
sir.
Yes, sir.
Okay, so let me give you one example here. Okay, I'm giving you one example for that reduction of this Boolean expression. Let us write down the example here. Number 1, f equal to a plus c, then ad plus AD bar plus AC plus C. Okay, suppose this is the Boolean expression you have been given, and I ask you to reduce this to get the reduced expression for f. You write down the steps required to get reduced function of this f. All of you apply the Boolean law what we have just discussed, and to get the reduced expression for f. If anybody having any doubt, just ask me. I am here to give you answer. Right? While you are trying to solve it, if you are getting any problem, just let me know. Okay, yes, any one of you have got the answer? Okay, Dhruv, Raj, Feni, Subham have given the answer. Okay, okay, let me show you. Raj, your answer is not correct. Okay, let me just do it. How can we do it? So here, first of all, what you can do, you can apply the rule over here in this too. You can take a common. Let me make a plus c as it is. So in this bracket, I can keep a common. So inside the bracket, that will be d plus d bar, right? Plus AC plus C. Now here d plus d bar, so it will be always 1, and that 1 will be with a, so I can just rewrite this formula, a plus c. I forgot to make bracket over here. At a plus c, in bracket here it will be a dot 1, right, because of d plus d bar. And here from a plus c and c, I can take c common, so it will become a plus 1, in bracket outside I can take c, right? So is equal to, here a dot 1, that means it is equal to a, so I will be getting here a plus c into a plus, here a plus 1, so it will be always 1, right? So it will give you 1 or c, like this, is equal to, now you can apply the distributive rule here, so it will be a plus ac plus, here it will be c. Now a into a, that will be equal to a only, and ac plus c, here that is what we got, ac plus c, that will give us the c only, here we have got. Same way this ac plus c, you can write down directly c, right? So that's what your answer is, f equal to a plus c, right? The expression or the proof which we are talking, that is for absorption rule, right? This is what the same rule is, the absorption rule, which we are having problem in giving proof. That is, here you can give in this way, that is, you can make your a common, and 1 plus b will remain inside, 1 plus b will become 1, and that's why it will be giving equal to a, right? That is the point where we will get confused in the earlier slide when we were discussing about rule, right? So this is the proof of that absorption rule with the help of formula. Okay, so are you getting all of you this? How can we do this? Hello?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so
Yes,
see,
sir.
this is
Yes,
right
sir.
now we
Yes,
have
sir.
just, okay, that's fine now. Okay, this is what we can have here, and now this will be making you to be more understanding about this rule and this type of reduction of expression only when you will be getting more practice with the more number of problems. So there are a lot many number of problems are given in book which is unsolved, and that you can take and just apply all the rules to get the answer, right? So that will make you familiar with this Boolean algebra reduction. Okay, so that's all for today. That's what we want to discuss for the Boolean algebra. Thank you very much. All of you, please enter your attendance. And yes, Gaurav is there. Hello. Hello, Gaurav, are you there?
Yes, sir.
Yeah, you were asking something yesterday. Is this what we had discussed today?
Sir, it has been solved.
What are you saying?
Sir, that query has been solved.
Okay, okay, that's fine. Okay, so all of you, please do all the thing what we have just discussed in the syllabus till now, because I think on 21st you are having the mid-sem, right?
Yes, sir.
Right, so all of you, please be prepared for that mid-sem exam. And those who have not been allowed due to their fee is pending, so please start paying that fee earlier so that you can be allowed for that mid-sem exam, and that will be making your evaluation part clear. Okay, so that's all from my side today. We'll meet again in our next session. Thank you very much. Have a nice day.